Good afternoon, good morning, and thank you for joining today's webinar with ETN Global on additive manufacturing. This is the second episode of our webinar series where we will go through the use of additive manufacturing, its applications in the repair and qualification processes. Today with us we have Nejib Chekir, I hope I pronounced it well, Manager of Materials Research and Development at Liburdi, a Canadian company specialized in additive manufacturing, a long-term member of ETN Global, very active, we could say. During today's presentation, Nejib will go through three key questions of additive manufacturing. So the first one will be, where is additive manufacturing delivering tangible value for repair, upgrades, or spare parts? The second topic for this webinar will be about the technological developments, so the qualification, certification, and the contractual barriers that have to be addressed somehow to enable the wider use of additive manufacturing. And then the overview of the repair market and how it did evolve over the last 3 decades. So with this, I'd like to give the floor to Nejib and also thank him and his team for today's availability to present. Thank you very much. Nejib, floor is yours. Thank you.
Thank you very much, Nicolo. So really happy to be here today and present some of the latest developments in the additive manufacturing market for repair applications mostly. So I'll start the presentation with a presentation of the Liburdi group of companies that I work for, to just give you an idea of who like I am and what the company I work for is doing. And then I'll present more in details the Liburdi automated welding systems line of solution to explain the technology a little bit more in details. I'll present the basics of the directed energy deposition technology, just because I'm, just in case you're not very familiar with the technology itself. Some technologies associated to the directed energy deposition in order to enable the technology, and some of the critical applications, and I'll conclude with an overview of the global maintenance, repair, and overhaul markets review. So I'm Nejib Chekir. I have been with the company for about 12 years now, with a background in mechanical engineering and materials science. I joined the company in 2014, so I've been with the company for about 12 years now, and I have completed my PhD in laser wire additive manufacturing of titanium 6-4, mostly for the aerospace industry. And I defended my PhD in 2018, and since then I've been a process engineer with the company and had the opportunity now to lead the team and became manager of materials research and departments within our team. So we're a Canadian-based company out of Hamilton, Ontario. So that's about an hour away from Toronto, south of Toronto. And over the years, this company started in the early 80s. But over the years, different divisions were created. And I'm really going to focus on the Liburdi automation welding systems that actually started around the 90s. But it became its own entity in 2001. We redesigned all the line of systems in 2017. And I'll get back a little bit about this history as well, including some strategic acquisitions. To date, we have sold probably between 200 to 300 machines globally. Mostly in the MRO world, but also in some cases in manufacturing of new components. So, usually I like to offer to stop at any point as well if anything is unclear or if you have already any questions. Like feel free if there is really a need to interrupt me, feel free to do it. Otherwise, I'll just keep going through the presentation. But what you see here is a line of systems that we manufacture to date. The idea between these is really mostly related to volume. That would be usually associated to the part that you're working on. The main technology, the basics of the technology is pretty similar for all of these directed energy deposition machines. And that is based on gantry style design. So that would be a gantry that can move the weld head, so the deposition head in X, Y, Z. Like the most basic system can be up to even 2 axes, I would describe it, as you see it with the dabber here, where it has only a Z and a Y component, for instance, or X or Y component. But typically it would be anywhere between 3 to 5 axes. So that would include typically a rotary and tilt positioner in order to achieve a pretty good positional control of the part of interest. It can get even much higher in terms of degrees of freedom that these machines can achieve, and we'll see some examples a little later. As I said, like the main difference is volume, working envelopes. You can work on parts as small as 1 cubic centimeter to parts as big as 1 cubic meter and even bigger if needed. The idea of and some of the advantages of having these platforms is that you can also work on the existing parts, right? So when we talk about additive manufacturing, we're especially of metals, obviously, it might be most of the time related to powder bed fusion processes. You might be more familiar with that process, but this process, directed energy deposition, is really more friendly with existing parts and the manipulation of existing parts. So it enables you to add features to existing parts in a more easier way. The other points with these systems, they can be both arc-based, so that would be typically plasma or TIG processes, but also laser-based. And you can see some examples here with the LAS 1000 FA, for instance, or the LAS 750, that have class 1 enclosures integrated to them as well. That means that you can operate with laser processes as well in a protected environment that enables you to use these laser processes without the need of additional personal protective equipment features. Like most of these systems, as I said, were application driven, and a lot of them you can use either wire as a feedstock or powder as well, depending on the process. So with laser, typically you can use both. With arc processes, it's mostly wire that's used with. Like any alloy that can be either formed into wire or powder form, technically, that means that you can use this technology and feed that alloy of interest into the melt pool to generate the repair or the manufacturing sometimes of new components. And to describe a little bit more schematically the process itself so that you have a basic understanding of what directed energy deposition solutions are. Typically you have, like in this case, I'm showing a laser head, but it could be also very easily an arc process, and some sort of feeding solution. So in this case, I'm showing a wire feeder, but you can imagine it could be also powder feeder. So, you know, bringing the material of interest, so that would be the wire or the powder, to the area of interest. The area of interest is where we'll focus the energy of the laser beam or the electrical arc in order to generate a melt pool. And then by the combination of feeding the material and moving the head in space, so in this case I'm showing in the ZX plane, but it can be in 3D obviously, and by repeating the process, depositing multiple beads, you can then generate a deposit in the area of interest that can be used for the repair or, as I said, sometimes in the manufacturing of new components. There are some key words here. The build-up direction is usually associated to the Z-axis when the weld head goes increments up and then deposits a new bead. Some heat affected zones that I'm showing schematically in red here. Just to say that when you're welding, you know, obviously it's a thermal effect, so you generate some isothermals that can affect one or multiple beads that were previously deposited, including the base material as well. So these would be the heat affected zone. They can affect your microstructure, which in turn can affect the mechanical properties that are associated to the deposited material. So in this case, you know, like when we look at some videos of the process, I'm showing two examples here of one is laser wire deposition on the left side that I mean, it's not very clear, but it's in the case of a repair of a blade tip. So that would be a high pressure compressor blade tip. And on the right side, you see the laser and powder process. In this case, it's for the repair area of a Z-notch low pressure turbine blades. Can be used, the right one can be typically used either in repair applications or also in manufacturing of new laser power, low pressure turbine components. In order to be able to enable these, you know, repair processes, excuse me, one very important point is really to teach the robot how to go in space. And we have two options in this case. One option would be if it's a very simple part geometry. So let's say it's a part that is only in 2D dimension, I would call it. And the blade tip repair is one example, or these caps that you can put on the bottom of some low pressure turbine blades in order to cap the root. In this case, we could use just a visual solution, so a top camera that can generate a you know, black and white type of image of the area of interest. And by using the contrasts that are generated in this image, you can generate sites of interest. Here, they're very small, but those would be sites of interest that were calibrated with regards to the position of your torch tip. And then by transferring that data, those site positions to the robot, then you can generate the, you know, like the tool path of interest and generate the repair or manufacturing again of a new component using this technology. Another solution for more complex geometries, those would be geometries in 3 dimensions. So that would be any complex geometry that include the XYZ components. In this case, what you can do is use a laser scanner that can generate a 3D point cloud. On the bottom left here, like you can see an example of a scan that was generated for low pressure turbine blades, the Z-notch area. And again, after calibrating this scanner to the torch tip position, what you can do is then generate these sites of interest that have not only the XYZ component in them, but you can include as well other degrees of freedom if they're relevant in this case, and that can include something like a rotary and tilt that teaches the weld head where to go. And by generating all these sites, then the robot will know where to go in space and to precisely position that the position heads and complete the repair of the part of interest. So 2 examples here. There are like a few other methods, also more manual methods, but this is what enables us to teach the robots where to go in space. Following the weld, so once you do the weld, there are like a few very important processes that can happen after the weld. And in this case, it can include post-processing in the form of heat treatments, for instance, or machining could be 2 of the options that you have post-welding. Machining mostly to get back to the geometry, the nominal geometry of the part. And the heat treatment typically is for stress relieving, very rarely to, in the case of repairs, to change the generated microstructure. And then other processes can be used as well to, qualify the parts. And this is usually based on either requirements from the OEM or when it's the development of new repairs, that's something that we can work together with, either the OEM or the supplier of the repair in order to define what our requirements are for a successful repair. And solutions like NDT, so that would include things like CMM or CT scanning, X-ray. So a few different methods can be used in order to have an understanding of how sound the deposit was. But also from time to time, destructive testing can be very useful, not only to have a better understanding of what typical microstructure was developed with, the developed repair, validate that microstructure, but also ensure that no detrimental internal defects would have produced within the deposits, and that could include things like porosity or liquefaction. It is always application-centered. When you complete all these processes, typically we can generate a report to keep track of everything that has been done. By doing these type of post-processing on an agreed amount of parts, you can then ensure repeatability of the process as well of interest. So when we go from the application, in order to enable these welds, what's very important is as well all the processes associated to these welds. They can include, as we already touched on some of the vision system, but you can add to the vision systems sensors that can provide very valuable feedback to the real-time deposit. And that can include thermal sensors on the bottom left here, where you could have thermal cameras or probes that can give you in real time temperature feedback of either the melt pool area or the surrounding areas in terms of heat affected zones. These can be stored in a log file as well, so you can either use it in real time or post weld in order to understand some of the key parameters that were associated to the weld. And that can include, as I said, some thermal feedback, but it can include things like typical laser power or arc power that were used, feed rates, positional information associated to the gantry or any other axis integrated in the machine. So they're extremely valuable for data logging and traceability as well of the different wells that would be completed. It includes as well in the special processes fixturing or deposition heads. So these typically are things that we would design in-house for custom applications. So the machine itself has a shared platform, but applications are very specific to the need of the customers. And in this case, you can see, for instance, at the bottom, some of the solutions we provide in terms of fixtures for high pressure compressor blades, so HPC blades, blade tip repair can be used as well for the leading edge repair, in rare cases trailing edge as well, or for the LPT blades. So in this case, you can see a fixture that's focusing only on the Z-notch and the shrouds perimeter areas. But you can also include the seals at the top as well. Excuse me, do you still hear me? I think my...
yes, we can hear you.
Okay, my microphone went out. Okay. But you can see as well the low pressure turbine as well case. And as I was saying, like you could add all the degrees of freedom to be able to tilt as well this blade and be able to work on other surfaces of interest if needed. Typically, these, as I said, like are custom designed by our mechanical group. And we have to focus as well on the shielding, typically around the areas of interest. Whenever we can, if we can focus only on local shielding, then we can design custom trail cups in order to minimize the downtime that you would have to purge the area of interest with inert gas. Otherwise, in some more complex applications, I showed an image of an impeller in the previous slide. In this case, typically a more global, a more general solution, shielding solution would be required, and that would be in the form of typically a gas box. And then special processes, we have more and more an interest from customers in some ablation technologies to not only some ideas, like that can be associated to this process would be pre-cleaning of the parts or post-cleaning following the weld as well. And some other applications that I haven't talked a lot about, but high pressure turbine components may require radial crack tips repair or the blade tip repair as well. And in this case, it generally includes induction heating in order to remove or virtually make unweldable materials weldable and prevent them from cracking upon cooling down from the melt pool to the solid phase. And in this case, that would, as I said, like include a typical induction heating coil that would preheat the blades, the area of interest at a specified temperature, and minimize that delta T in temperature between the liquidus of the melt pool and the solidified end temperature upon cooling down. And these again can be automated, so can be integrated in the platforms that I've shown earlier and be automated into repairs. As an example, one very common example is blade tip repair of high pressure compressor blades. In this case, you can see it's a LOS 500, but we have sold LOS 500 and LOS 1000 platforms to be able to achieve these type of repairs. And what you see here is the plasma arc welding process on the left side, two repair stations. So when one is welding, you can load the other one as needed. Wire feeding solution, top cameras to be able to generate the sites of interest. And, you know, like this solution pretty much was integrated in the first machine that we sold for this type of application was in the early 90s. And since then, this platform really is one of, you know, like the typical platforms currently used in directed energy deposition repair of blade tips or leading edges. And, you know, like millions of components have been processed since then. These machines run 24 hours a day, typically 3 shifts a day. Highly automated and highly repeatable repairs. Most of the time we use either nickel-based or titanium-based alloys for these repairs. And, you know, like over the years, the solution is very customizable, so you can adapt it for different blade designs and you know, like up to the latest gas turbines designs are being processed currently on this platform. Here, like it's a CFM 56 HPC stage 1 blade tip repair on the top left there. When you know, like that's one example of an application, typical application regrouping all this automation, but you can even increase the level of complexity, I would call it, of the automation by integrating even other sensors and improve the traceability as well of your process. In this case, you can integrate things like optical character recognitions for, you know, automatically saving any serial number associated to any part into the weld schedule of the specific part. You can use RFID tracking as well in order to understand, you know, like follow up, you know, the states of the machine and of the components being repaired. And then through technologies like OPC UA, for instance, this is a software solution that can connect the machine to your own internal network. And that allows you to retrieve any key parameters from the machine directly to your network. And that enables you in a way, you know, like big data. So you're able to use any data that's generated by the machine that would be including, for instance, thermal feedback, the weld monitoring, so any videos of the weld itself, the serial numbers, all of that can be combined, and then you can use, you can present them into a chart form. This one is one of examples on the bottom right here of the slide. Where you can track then key features from the machine and you can know if you had a fleet of these machines in your shop floor, then you can see which machines are operational, which ones are down, and so on. And so you can use all that data to not only do preventive maintenance, for instance, but also to have a live picture of what's happening in your shop floor. And with this type of solution, you can then select a specific serial number, for instance, for associated to one part, and then you can retrieve all the data for that specific serial number, including thermal camera videos, weld monitoring, and any deposition parameters that were associated with that specific part number. When you do that, then when you combine all these different solutions, then you can end up with a highly automated platform that can have, in this case, it's well above 5-axis degrees of freedom, where you can combine all of this together, and all the operator has to do is load the unwelded parts. The machine can recognize which parts were welded or unwelded, and do all the process where it will load the part into the fixture of interest, rotate it to the welding platform area, generate the size of interest, use the the welding program to generate the weld, and then bring back the welded blade to the arm location, and the arm will retrieve the blade and put it back in its nest. And as I said, like, all the operator has to do is load or unload the blades, and everything is fully automated, and with a focus on traceability and the history of whatever repair has been completed. In this case, it would be for low pressure turbine Z-notch repair. I have, I'm not going to show the video. There is a video on our website of this specific process. I have a link below the image here that you can review on your own as well, if you're curious about the whole cycle for this process. So I'll conclude a little bit with, like, an overview of the market and what this means in, like, I've shown already that we use this technology for repair applications. But here what you have, and before I get to this graph, I'll give a little bit of kind of a very brief history of what happened in the 30 last years. But in the years 90s, 1990s, 2000s, like, a lot of the repair was mostly outsourced from the OEMs, and the focus was mostly on trying to standardize repair applications. But then by the years, like the 2010s, a lot of the computer power available opened a new field of automation that enabled digital data, and like, the use of these automated solutions more reliably. The OEMs mostly tried to expand their repair capabilities more and more during that time, and like, the complexity in the engine designs increased substantially, which kind of pushed also more so the demand for automation and ensuring that you can trust the repair that you're achieving, and minimize any scrapping of the components. And then by the 2020s and up to today, we had a rapid COVID recovery. We're seeing aging fleets, which increases the demand for repair, and low supply in a way. So there is a lot of competition in order to try to get your hand on these gas turbines. So it increases the demand for increasing, like, the repairability of the existing gas turbines. And you can see here, like this was more like from the 2015, where they were trying to forecast the typical market demand for maintenance, repair, and overhaul of gas turbines, and it was a market that was in the high, expected to be in the high $70 billion in 2017, and the estimation was for this market to grow to above $100 billion by 2027. And you can see even like an estimation here in 2022 that was just above 80 billion. But when we look at some of the actual numbers, and on the left side here, in 2022, we can see that we were even closer to almost 100 billion. And it probably would have been even higher if you discount COVID that happened. But the forecast now is for the next 10 years coming up is really in the range of 120 to 150, depending on which consulting firm would produce the data. What you can see, what's very interesting as well, is that it's estimated all the time that in these MRO, and that focus mostly on the aerospace field. Obviously, when you add the industrial gas turbines, it probably will increase even more substantially the numbers. But the idea is that in this case, 40 to 60% of the business is really focused on engines. So half of that money is really focused on repairing of the gas turbines. And that means that this market really has like a very big growth potential, and especially with the latest technologies that are coming to market, and with the push for the energy transitions, and the demand in even more power, driven by AI technology, for instance. In that case, there is a high demand on the market right now to have your hands on a gas turbine, but also being able to maintain your fleet and have available repair processes to increase the life cycles of the components that you're using in these gas turbines. So it's kind of a summary, very brief summary of the market look. And on that, I would like to conclude this presentation by focusing again on some of the key points that we reviewed. So these are standard machines, directed energy depositions, but highly customizable for your application of interest, and focus mostly on blade components, but there are other applications as well on liners or casings that can be of interest as well. Blade hubs and the likes. This process is very friendly for repair applications. I've shown you some of existing applications, but there is a lot of work to improve the automation and improve the amount of time control, but also the feedback you can generate and the data you can generate from these machines. Some applications are focused on the manufacturing of new parts, either as a step or the actual manufacturing of the whole part itself. I haven't touched much on that since we were mostly focusing on the repair applications. And there is a wide range of available feedstocks, that you can use with these processes. So that's definitely a big advantage of the process, and especially if you use something like wire. Typically, you can generate defect-free build-ups more easily than if you were using powder. And then all the push on the big data and connectivity as well associated to this process, and an overview of the current, market and forecasts for the next upcoming years. So with that, I'd like to thank you for your attention, and if you have any questions or if you want me to go back to any slide, I'll be happy to answer any questions. And sorry if I took a little bit longer as well than expected.
Thank you, Nejib, for the detailed presentation. We propose to open the floor for question and answers from the audience. So please, anybody, feel free to, please. I see Luca first, and then I see, okay, let's start with you, Luca. In the meantime, I just put the link to the survey for everybody to complete.
Okay. First of all, thanks for the presentation. Very interesting.
Thank you.
So I am from Additive Manufacturing Florence team. I have a question, a curiosity about, for example, the repair of turbine blades. No, when you, for example, add material on the tip by this process, if a let me say post welding treatment is required on the component, no, what happened to the already machined part with very tight tolerances, like for example the foot of the blade? We are sure that all the machined part still remain in tolerances. We check with dimensional method like, I don't know, CMM or light scan, something similar to check the geometrical tolerances.
Yeah, it's a good question, and that's part of the one of the slide that I had. Let me know if you can still see my my screen. But like what's very important is to be within the accepted repair specifications that are typically shared with us by the OEMs in general. And like when you develop the repair, typically you want to minimize the distortions that could be associated with the repair process. In that case, something like induction heating can be beneficial for that, especially when we talk about turbine blades. And then you use typically non-destructive testing to ensure that all the other key elements, including the position of the root, are within spec. So typically when we do this, we're one of the steps, in the repair process. What we would do is help our customers typically develop the welding process. So in order to deposit enough material on the blade tip to generate the geometry of interest. But then we work typically with our customer as well. We have all the NDT in our site, to understand what the acceptance criteria are and ensure that we always fall within those acceptance criteria. And if we're not where we want to be, there are different ways to try to a lot of different deposition parameters or welding parameters that you can affect in order to in an attempt to minimize the distortion, for instance, in this case.
Okay, thank you for the answer.
And the process is currently used, just to be clear as well.
Okay.
We have it's mostly in the so our machines are mostly for the aero engine gas turbines styles. So we have currently machines that are doing these blade tip repairs for turbine components. We have a few machines as well for IGT, mostly focused on IGT, industrial gas turbine components. So bigger buckets, I would describe them, that successfully pass the repair as well.
Okay, thank you.
Vladimir, please, if you could go briefly. Did you hear us, Vladimir?
Okay, can you hear me now?
Yes.
I already was talking for a few minutes. Yeah. Nejib, thank you very much for presenting materials. It's quite interesting to see. So you, as you mentioned from the beginning, you mainly focus on the DED technology. But my question is regarding the, let's say, another technology. Like, are you using to a certain extent, and if yes, to what extent, a so-called coupon approach, when you can, let's say, pre-manufacture piece of the, let's talk about the veins, for example. We can have a damage of the leading or trailing edge, and then you prefabricate this damage element and then brace or weld it to the, let's say, to the components. This kind of approach, to what extent it's, let's say, developed in Liburdi?
So it is so we're talking about not welding, but really adding a patch, for instance, right, of material in the area of interest. Is that the question, or?
No, I'm talking about even to add the part. It could be big portion of the leading edge, for example, or big portion of the trailing edge.
Yeah, and that would be a patch, not a welding repair, right? Like that you weld to the leading edge, for instance.
No, it will be like, it will be, first of all, you will remove the damaged part, then you have a prefabrication of the removed part, and then you will do the connection, and then joining will be brazing or whatever. Welding.
Yeah. Well, we had this request, and it's mostly associated to older engine types that we've seen, where there is that typical request of doing what you described. So it would be removing a whole section of the blade and then rewelding the area of interest. But like that would be mostly like a butt joint, for instance, that you re-weld two parts together and then use that to remachine the area of interest, either by brazing or welding. What we've seen is usually with the brazing is it has lower mechanical properties in general than the actual base material or the like the part that you're brazing onto the blade. So it becomes kind of a weak point, and that's something that our customers are not very keen on most of the time, and it also depends on what approved repair is enabled for a specific part. So if that's the only repair that is approved by the OEM, for instance, then you don't have many other options. But if you have the option, typically by doing an additive repair can be very beneficial, especially with now we have, I haven't shown it on this presentation, but we have processes now and technologies that we're attempting to integrate as well to the repair in order to help refining the microstructure and achieve either equivalent or better properties than even the substrate. There are pros and cons for different approaches, and in general, what we try to do with our customers is to identify which ones makes most sense. Based on our experience as well, we can suggest different approaches, different technologies, different like power supplies or feedstock material, and then we can suggest a repair route whenever possible. I hope that answers your question.
Yeah, you did answer my question. Thanks.
Thank you.
Thank you, Vladimir. Then we have another raised hand. I cannot. Lokesh, please.
Yep.
Go ahead.
Thank you. Thank you for the wonderful presentation. So I'm Lokesh Chandrabalan from Baker Hughes, from the Additive Manufacturing team. I have a question related to, especially the repair process. So the first question would be, do you experience any sort of, you said you would be creating a sort of patch, so which means that we have a turbine blade in this case, which has already been functioning, and then we have a certain surface to which we need to align and then reconstruct the rest of the parts. So in that aspect, do you experience any sort of misalignment errors in certain order of magnitude, and how do we guarantee the material integrity, especially in that zone. So right from the mechanical properties and also in terms of the functionality of the blade itself. So the residual stress is also handling the residual stresses arising from the process itself. So how could this be handled in a way or the other? Are there any specific tests that could be done, or how it could be validated?
No, really good questions. Thank you for your questions. And to start off, positional accuracy. So I haven't really stressed a lot about it, but if you still see my screen, I guess, these gantry-based systems, we like to go with this because we work closely with the supplier of these gantries in order to ensure any deflections that can be associated to the gantry itself just naturally. But also we use these linear encoders that are precise to, very precise is within 25 micron or lower, that can give you a very high accuracy of the positional feature of your deposition head. So what we do then is we, once you have the machine built, we commission it and we use these laser technologies that can provide you with what we call compensation tables. So the gantries that you purchase usually have an inherent, deviation by essence. And then we measure that deviation using highly precise lasers that can give you feedback like linearity, the squareness between each axis, the dimensional precision. So when you move 1 inch, it's actually 1 inch to the micron. Sorry, so I'm used with the imperial here, but if you say 20 millimeter, you'll be at 20 millimeter to the micron precision, and that combined with the vision technologies that I described earlier, that also can generate very precise sights based on a calibration procedure that we developed as well in order to relate the data from this vision technology to the gantry position. Then you can achieve highly precise positions using this technology. So that's, to understand where to shoot in a way your laser and feed the powder or the wire. The other thing is then, how to ensure that you meet the specs in a way, if I understood the rest of the question. And that is through welding development. So most of the time our customers will ask us to develop the weld meeting the specs. So that would be in terms of microstructure, mechanical properties, or also dimensional. And in that case, what happens is that we will develop the weld, so find the proper welding parameters that can generate that sound buildup. That is a process that can take anywhere from 2 weeks to 4 weeks typically. And then once you have these welding parameters, they're kind of locked. So you qualify the process with that, with a batch of representative parts. So sometimes a customer could tell us to, we weld 100 parts and ensure that 95 of them are good, for instance, to give you an image. And those 95 will go through destructive testing to just ensure everything looks good in these parts. So that would be one way to ensure that the weld looks good on the part itself, and then you can add, more advanced characterization techniques to understand anything from dilution to, the different phases that can develop in that deposited weld, and then you can use also the CMMs or the X-rays to validate that as well. Once the weld development is complete, typically what happens is like a weld schedule. The parameters are locked and the combination of calibration, verifications on the machine that can happen anywhere from weekly to monthly to, every 6 months, will ensure that your machine produces a repeatable weld as well in the area of interest. And the combination of the vision system and the precision of the gantry can, and the search boxes that tells you where the sites of interest are on each part, can handle the variation part to part as well that can be seen in the case of repaired components. It's very different from new castings or new manufacturings, where you can see variations, sometimes acceptable variations up to, let's call them 20 thou. So that would be almost like half a millimeter sometimes in some cases.
Thank you.
Thank you.
Did that answer your question? Yeah.
Yeah. Thank you. Thank you very much.
Thank you.
Jan, please.
Yeah, thanks. Thanks very much for your interesting presentation. Question I have is also relates a little bit to the previous question is, do you apply non-destructive testing techniques to, check for surface defects, but also the subsurface defects?
Correct, yes. So a lot of the cases, we have RT requirements. So that would be either X-ray or micro CT to be ensure. Most of the time is to in order to try to check if there is any linear defects or internal linear defects or porosity. Fluid penetrant inspection is combined as well with that. So that would be for any external defects. So that would be cracks, porosity on the outside. Those I would say are the main ones for NDT, in addition to CMM, but that would be more for the dimensional
for
side.
the geometry. Yeah. And then second part of my question is, do you have certain areas of the blade, for example, that you will repair and certain areas you will not repair? And what is your guidance for that?
Good question. Yeah. So definitely, it's very important. So there is acceptance criteria typically on how far you can repair. So blade tips, you will have usually a maximum height that you can. So before the repair, you have to machine the blade down. So there is a maximum depth that you can achieve to machine the blade tip. On leading edges, it's usually an area as well. It's typically associated to low stresses areas. Once you get to the higher stresses areas, like it becomes very either the blade is scrapped directly or it's just not, it's not repairable most of the time. But those areas are either defined by the OEMs typically, with the safety factor obviously, but those would be defined typically by the OEM. But we have in-house as well engineering teams that can, if you don't know it, or if it's a legacy engine that doesn't have data anymore, we have the means as well to use our team of engineers as well in-house to help you define what some of those areas could look like.
Thank you very much. And then if I may, last question, do you have a certain international standard that you follow for the welding process?
Yeah, there is AWS 17. I forgot there is American Welding Society standards that we follow a lot. So that would be mostly, like in terms of you'll have different levels where you can have different levels of how sound your weld needs to be. So that would be a common one. But what we see a lot is not just using these international standards. Those are kind of the baseline. In addition, we get a lot of the internal or OEM specs that were generated based on their own internal research, and those are usually even stricter than the ones available publicly, just because it just addresses their specific needs, right? And it can also add testings that are not typically shown in the normal specs, where you would have, it's almost like an engine run, or like it's just like trying to check if the blade can resist at high RPMs and high loads, so there is like custom specs that we have to abide by. And then if you look as well at the feedstock, so the materials, so those will have typically to also follow some very stringent specs, mostly in the aerospace field. In industrial gas turbines, there are ways, depending if you own the engine or not, like there are ways to maybe even develop your own repairs as needed. But that would be more at your own risk.
Yeah, thank you very much. Yeah, much appreciated. Thanks.
Thank you.
Thank you, Jan, and thanks all who participated in the question and answers session. We are going slightly over time. So if there are further questions, we would be happy to receive any of your comments or questions by written email to our ETN Global inbox, and we'll be happy to put you in touch with Nejib and also his colleagues at Liburdi. With this in mind, we also have to organize. We'll organize further webinars.